All right, let's do both. Did she? That's because Paint Crew has a reputation. I'm sure that's why. All right. So I'm gonna do the limit from the left, and then I'm gonna do the limit from the right. And if they are the same, then that means the derivatives are the same, and that means it's this. What? H always goes here. If you do the alternate formula, it's X and A. Yeah, that's all. You want me to do alternate instead? What two variables do you stand for?
Whatever we did, it was only like 2 eggs, and that was it. Never did.
F of x minus, f of a over x minus a. That's the alternate formula. A is the x that you're approaching. So this is the alternate. Both of these will get you the same thing. No, you can. The A is always the number that you're going towards. Like this is not X anymore. This is your A whenever you're in the alternate form. Okay, both of these, all right, listen, both of these are going to give us the exact same thing, right? Your choice on which one you use. Yeah.
Oh, wait, are you talking about the formula?
Yeah, the two formulas. Okay, so both will give you the same thing. You decide which one you'd rather use. I prefer the difference quotient, the one with H going to 0. That's the traditional, always been around, always done. That's the way I learned it. It makes sense to me because I envision that distance between those 2 points shrinking down to 0, and so that makes sense. Remember how we derived it with the slope between the 2 points, and as we close that distance up with the f of x? Okay. I'll show you both ways on this one. The other one I'll just do one way. All right, if I go to 1 from the left, that simply means this is the equation I'm using, right? Well, from the right, I would use this bottom equation. I'm going to plug in every little step of the way here so you see what's happening. No, you're not. 1 plus 1, so minus 2. Remember, for this, I'm going to 1. I can factor the top. X plus 2, x minus 1. Remember, what's the goal? Not 0, but 1 this time. Well, 0 with the other formula, yes. All right, I can plug it in. What do I get? 3. Just to prove my point, if you use the alternate formula, you have 1 plus h squared plus 1 plus h minus over 8. I'm going to 0 this time. Difference quotient. That is correct. Two and 1. I got h plus 3. So I get 3. I get the same thing. Okay, wait, no, this is still the same. This is the same thing works 2 different ways. So whatever way you did it, if you use difference quotient, if you use alternate formula, you got got the same thing. But the question is, does that match the right-hand derivative, right? Alternate or difference quotient. From the right. That means I'm using this one. So f of h plus x minus f of x. I have to write it to see it. Oh, it was down here, I guess. But thank you, Sylvan. 3 h plus x minus 2. It doesn't. Okay. Yes? Okay, I'll turn it around. Minus 2 minus 3x plus 2 over h. 2's go away. 3x's go away. One of the h's. I did get 3.
I mean, I can make up what is numbers. I can write it. Why they're being.
Oh, wait, I didn't put 1 in. It says at 1. You still get 3? Oh, you do. Yeah, I say it's 3. What else in your homework?
Can you actually do 38 though?
They do match though.
38.
29 and 38.
I didn't understand it.
Hey, yeah, question about the table. Why did I always have to divide by that one text?
Okay, let me show you. Let me do this way so you can see it.
You didn't make it stop to do homework. I submitted it. I submitted it at 8. It said 8 a.m. I know you forgot to move it. Yeah, because you didn't put it on.
All right. If I'm fine, who asked about this one? Okay. Okay. Here's what I'm doing, and I think that maybe this will help you. I am, if I don't, if I asked you to find the instantaneous rate of change at 7, when x equals 7, and this is all I gave you, there's no way to find instantaneous here, right? Do we all agree?
Yes.
But I can use AROC to estimate the instantaneous, and that's what I do. So IROC can be estimated using AROC, but I surround myself around that particular value. So for instance, if I said when x equals 7, then I would come here and I would do AROC for these 2 points, right? What? I'm just saying, I'm trying to tie this back to this question because this is what I was trying to get to on Friday. Okay, so now if I go back to this question and they're telling me to estimate IROC, so I'm going to go through each point, and for here, for instance, I would do the difference in y, which would be 0.33, divided by the difference in x, which would be 1. This is going to be my AROC or my IROC estimate. Yes? Oh, 3.3, sorry, because I looked at it. Right? What? It's 1.
Why, what's wrong?
Same thing that's wrong with me, apparently. We can't see it. All right, so you do it for the whole table for each one, but what's happening is you're forming these coordinate pairs, right? So I go halfway in between this. So my new x is going to be 1/2, and my y, this is my AROC. So this is going to be 3.3. My next point, I include the last point I used and go down 1. So now I'm at 1.5. Bro, it takes like 2 minutes. I'm going in between 1 and 2. Going halfway in between 0 and 1. Then I'll go halfway between 1 and 2. Then I'll go halfway between 2 and 3. Then guess what I go halfway between? 3 and 4. And then I go between 4 and 5. And each time I take those and then I do the slope between those 2 points. So now it's 13.3 minus 3.3. There's a 10, Wyatt. What? 2.5.
So that's
That's not what I'm looking for. I'm looking for the derivative of the whole table.
Okay, so what do we do with it?
You'll see today. We're going to work on graphs today.
So we totally did this for no reason.
Dang. Dang.
I just put on that homework. Literally.
What 0 and 10 are you talking about, Logan?
You're making those things. Why you're doing that? Look, he's not doing all of it. He's talking about the first row on the last row.
You can't do that. That's not what we're not finding an overall derivative. We're finding. I understand what you're saying. I understand what you're saying.
Look, I did it and it gave me the right answer, so I don't know what you're talking about. Look at this. Where is it? Right there. See?
No.
That's what I did.
That's, can you guess an equation for the graph of the derivative? That is not.
That's the slope.
Go sit down. No.
That's the right answer.
Go sit down. Go
How
sit
is that
down.
not right? How am I not allowed to do
All right, because that's not what the question asked you to do. All right. Moving on. All right. We are moving forward. And we're going to graph, we're going to compare today, we're going to compare the function itself to its derivative. Yep. All right, guys. We were finding the derivative in between, we're finding the AROC between each point. And then you had to answer, guys, I am struggling with you all today. I have been nice and understanding and patient, and I am losing my patience. I am trying my best to get through this for you all. We are 25 minutes in, and we are still kooky, and I don't know what's going on. Bro, the game was Friday.
That doesn't matter. That doesn't matter.
David? Where is David? Where's it at? I need to borrow that a second. What did it say? So it said estimate the equation of the line, right? Can you guess an equation of the derivative? After today, you won't be guessing. You'll know how to do it. If I did, I couldn't give it to you. What? I'm going to show you this little piece, and then we're going to move forward to differentiability. And I'm going to show you how to do it on the calculator. We missed a step away. Slope of the tan line. Give me another synonym. Anybody? Hi, Rod. Give me another synonym. Slope of the tan line. What formula? Difference quotient.
dy over dx.
dy over dx. Somebody asked, I don't understand what a derivative is, so I'm listing out what a derivative actually is. Because we call it so many different things. The limit as x goes to a, f of x minus f of a. The point that I'm getting to is all of these are synonymous, and you should know them as such. Probably the most important one, in my opinion, to understand would be knowing that the derivative is the slope of the tan line. This is how you find it. Whoa. How you find it. This is notation. That's what it is and what it is. Huh? Is it not Wyatt? Sorry. All right, today is called this is part A of the next part is differentiability. And we're going to start with graphs of derivatives. All right. I want you to think about something with me for just a minute. This is a big topic, and this is something we will revisit as we go on forever and ever and ever until the end. You will guaranteed one of the FRQ questions is going to give you a graph, and you will have to think about what the graph of the derivative looks like, or vice versa, and you will have to do some interpretation. It never goes away. So let's think about it for just a second. I'm going to start you off with a graph of what's something we have found the derivative of recently. What was the derivative of x squared? What does the graph of x squared look like? A parabola. A U. Right? Trying to think of the easiest way I can kind of explain it. All right, f of x. I didn't want to. Okay. If I want to graph the derivative, remember what the derivative is. It's what? Slope of the tan line. So let's think about this for just a second. I'm going to put some random points here. Knowing what you know about parabolas, this point is 1, 2. This point would be 2, 4. Negative 1, 2. Negative 2, 4. Everybody okay? Here, if I draw my tan line, and I'm just going to put several tan lines on here. In terms of the slope of these tan lines, tell me what you know. Bless you. Okay, they're all different, but specifically, let's describe them. Here, this one's easy, right? That looks like the slope would probably be 0. We all agree? It's flat, right? All right. As I move over here on the right side, my slope is definitely positive. My slope is definitely positive. Agree or disagree? Okay. Bigger or smaller as I get bigger on x? Because my slope is steeper. Does everybody see that? So here, as x gets bigger, would you agree that my slope gets bigger also? Do you see why? If I continued, bless you, to make my way up this parabola, that slope would be even steeper and it would continue. It would be approaching that undefined, but it would never get there. But it's getting steeper and steeper and steeper. So the slope is getting bigger and bigger. Now, as x gets smaller, what's happening to the slope? It's getting smaller, but instead of smaller, I'm going to say m gets, it's still steeper, right? So I'm going to say bigger negative. Just to kind of help you see, bigger and negative. This is not really mathematically correct. Now, we know that the derivative for this is, I need another color. Two x. Would it make sense? You can't even see that very well. Well, we have found this derivative before. Right now I'm just showing and comparing here, but in a minute, we're gonna actually graph one from scratch. Would it make sense that this is the derivative graph? At 1, the y value is pretty big. So I'm describing the slope, in other words, is what I'm doing on this graph. At 2, it's even bigger. At -1, it's big. At -2, it's even bigger negative, right? Do you see what I'm saying with this? So as I ease, it's a constant increase here of where I'm going. So the derivative is linear. Does that make sense to you? Some of you are looking like, no, that makes absolutely no sense. And some of you are like, I kind of see it. Okay. As I move this way, my slope is getting bigger, right? So thinking about the same x's and letting y be my slope on my derivative graph. So here maybe the slope is 1 or somewhere close to, or 2. We'll say 2. Here the slope is like 2. That would mean here the slope is a whole lot steeper, right? So maybe that slope is like 6. So 2, 6 would be here. And so as I go on this line, anywhere I go on this line, it would tell me what the slope of the tan line was on the parabola, right? Okay, let's look at another one. Let's do one you can easily see. Yeah. Let's take y value. Y value. All right, here's my function, and I want to graph this derivative. Now, I hope somebody sees this fairly quickly. What do you know about the slope of the tan line? Everybody agree? Anywhere you go, the tan line's the same. The slope of the tan line's going to be the same. So that means my derivative is going to be a constant. Would that make sense to you? The derivative is always the same, no matter where you go. Let's say this is 0, 0, pretend. Let's say this is 2, 1, just for the sake of example here. What would the equation equation then of my tan line, of my derivative? Why? Rise over run, you're exactly right. It's the slope of the line. That's right. So my derivative is just 1/2, so my derivative graph looks like this. I didn't completely ignore this graph here. I guess that's not it. That's the wrong equation. That's why. There you go. Yes. Each point, guys, y'all let me know when y'all are ready. Each point on the graph of the derivative literally represents the slope of the tan line at that point. So if I come here, if I were able to find IROC right here, right? So I went back to that very first example right here, right? If I were able to find IROC at this point, the X value stays the same. My Y value would be IROC at this point. So IROC when X equals 1, which I'm going to estimate to be here about 2. No, we're talking about what the graph of the derivative would look like based on the graph of the function. So, what? Same one. All right, here. Of the derivative, yes. When I graph the derivative, when I graph f prime, I am graphing the x value from f of x, and I am graphing the IROC of the derivative at that point, of the function at that point. So here, which is the slope of the tan line at that point. That's the derivative. Does that make sense? Y'all are looking at me like no. Tan line's the blue one. Let me show you an example, a picture. Yes, yes. Slope of tan, yeah. All right. Look at this graph. The graph of what? A cubic? A cubic? All right, so if I want the graph of the derivative, I want you to look at what's happening with the derivative here, right? Derivative, I'm thinking slopes of tan lines, right? Sorry. All right, so I know within this value, my slope is getting closer and closer to what? 0. We all agree? Okay, approximately. Yes? All right. As I move to the right, what's happening with my slope? M is increasing fairly fast, right? But it's positive. Agreed? What's happening over here? Is it decreasing? Look, as I move left to right, it's still positive. M is still positive. What's the slope? Each of these little lines, what kind of slope do they have? If you draw little tan lines, If I just drew this line right here, would that have a positive slope or a negative slope? Positive slope. Okay? It's still positive. So I'm thinking, and look, it's evening out. So it starts out, so I'm going to think really steep, then to 0, then it starts getting really steep again. Yes? No, because your x values are different. So this happens when x is -5. This happens when x is +5. So look at my choices here. Could A possibly be that graph? No, why? It's going negative here. This tells me that the slope is negative, which doesn't happen in mine, so that could not be the graph of the derivative. Is this below the x-axis? What? Give me the coordinates of this point right here. -4, negative something. That something doesn't even matter. Because over here, up here, what's up with my derivative? What's the slope? The slope is always what? Does my slope ever go negative here? No. So I can never have a negative y value on my derivative graph. The y value, these are derivatives I'm looking at, and for derivative, it's x value, and then it is slope of tan line. Okay, I am graphing the slope of the tan line. So A cannot be it. Do we see why? Not really. Okay. All of these are positive, yes? Do we all agree that? Can we all see that? Can we all tell that all of these are positive? And right in the middle is where my slope is kind of leveling out. So I'm starting out really, really big. I'm coming in close to 0, but then I'm turning around and I'm starting to get bigger again. Do you see that? Look at my slope values. If I gave values to these slopes, yes, slope value. Okay, now the graphs that you're talking about, these down here? Okay, no. This is the graph of the derivative. The derivative is the x value plotted with the slope of the tan line. Yes, you see how it.
I mean, I don't understand why, but.
So it would be B.
Okay. It would. You're exactly right. It would be B because, look at it. Look at what's happening here. Let's look at some points. When x is -2, y is positive. Is that's what is happening over here? When x is -2, is the slope of the tan still positive? Yep. How about if x is 4? If x is 4, yep, still positive. You see, if I was over here, though, when x was -4, y was negative. Yes. So, look. Think about if I asked you to find IROC at every single one of these points. Okay, so what if I said, what is IROC right here? Okay. I'm asking you to find the slope of this little teeny tan line. Yes? IROC here would be the slope. Same thing here. Same thing here. And then what I asked you to do was plot each of these points as x against the slope. Okay? So this was IROC at -3, right? This was when x was -3. And maybe you got, I don't know, maybe you got 8 for the slope when you found IROC. That means you would plot the point on your derivative graph of -3, 8. negative 3, 8. And then if I came here, I'm just saying if I found I rock, if I use that difference quotient, I would have to use that difference quotient at each of those points. Or I could use the difference quotient to find an equation in general. You're just understanding. You're going to have some really, really wonky graphs that look maybe like this, and you'll have to graph the derivative of that. Or that's the derivative, graph the function. So, all right, so look, each one of these, right? That's what I'm plotting against. I want you to see why. Look at C. Why could it not be C? Because this would say that the slope of the tan line is negative here because the function value is negative there. Yes? But it's not. Same thing for D, it's going negative, right? Well, it can't be A because A goes negative also. It doesn't?
Wait, can you do another one?
Okay, let's do another one. It's not, I am using different colors, but it's not showing up. All right. I'm listening. I'm estimating in. I'm estimating. Let me try it this way. Let me try this. Yes. I am not even going to give you choices here, and I'm not even going to give you an equation. I want some estimates, okay? All right. Here's what I'm going to do. I want us to sketch a graph of what we think f prime of x might look like. So here's what I want to think. I'm just going to come in here and kind of do this a little bit as I come around. I don't need specific values. I just want to think generally, conceptually, right? Over here, my slope is negative, yes? And over here, my slope is positive. And then it's 0. Okay, the 0 is easy. And maybe if I graph them above and below, this will help you a little bit. All right, look. All right. At 1, look at 1. My slope is definitely positive, right? I'm just going to put a point up here positive. I don't really care where it is right now. I just want it up here positive, right? At 2, is it still positive or is it negative? Is it a bigger positive or a smaller positive? Bigger positive. Okay. So bigger positive. How about at 3? Even bigger. And when I say bigger, I'm talking about the y value, yes? Okay. So it's higher up. Okay. Go to the other side over there. What's happening? It's the exact same thing, but it's the negative of it, right? So whereas this one was here positive, it should be same place but negative over here. Would we agree? Because it's the same on both sides. So same thing at 2 and same thing at 3. I would say that's a good estimate of the graph of the derivative of that. So that's how you would. So anywhere I go on here, if I said, Kaylin, using the graph here that you have, what do you think the derivative is at 2? Why? So, even though I don't have even though I don't have an equation here, I can use it to estimate that particular value. This is not going as well as I thought it was going to go. Okay.
Wait,
Look at.
Wait, can you go and give us our sheet? And I have that sheet of paper.
Yes, I have copies. Oh, yeah. Yeah. Yeah.
You are not above the law.
All right, look at number 3.
Nobody asked you to.
All right, look. This is still a cubic. Hey, guys, that is enough. The class is not falling apart. I am still in control here. Have y'all seen it? I am still in control. Okay. That's not up there.
Wait, can I do? I want to work one.
What the actual heck? Wasn't it just up here? All right. What's happening here? Negative slope. Again, here is negative. So I know between those 2 points, I should be below the y-axis, right? And then here. Okay. How do you know, Sullivan, that it's an upside down parabola and not a right side up parabola? All right. So look what's happening. Oh, I got too many choices now. So my slope is negative. My slope is negative. That means, in terms of my derivative graph, I'm below and below, right? Between -2 and 1, I'm positive and I'm above. Yeah. All right, look at A. Could A be the graph of the derivative? No, because it doesn't go below, above, below. It's always negative. No, I'm trying to teach you how to recognize. But you will have to sketch the graph of the derivative on your own without choices. All right, this is below, above, below. But let's just make sure. Below, above. All right.
Let's do that homework.
If we have a quiz.
Yep, we need a vertical house.
All right, do not blurt out the answer. This one's funky. Can't come out anymore. All right. Take a look, take a look, take a look, and let's talk about it in just a second. Look, make your decision, but don't tell anybody what your decision
Wait,
is.
hold on. What is it?
That means something. How many of you think it's A? Raise your hand. Slade? How many of you think it's B? Couple people. What about C? D.
Daddy, baby, let's go. I think it's B, Mr. Hughes.
All right, let's do some analysis here. Slope is increasing and increasing, yes? What color did I do the other? The pink one. Slope is decreasing, slope is decreasing. Right? So I need to be above, below, below. I'm sorry. Oh, looks like you wanted to kill me for a little while, but you still haven't gotten it quite wrong. All right. Okay. Look.
How is that top left below? Wait, and how is it negative?
Tan lines. They're negative slope. But they're still negative. It'd still be a negative slope. All right, look. I can't have a derivative where I don't have graph. That's important to note. There's no graph here, so they can, right. So I can already mark out A and C because I can't have a derivative where I don't have graph, right? So above, below, space, below, above. Look at this one. Above, below, space, below, above. All right, I got one more thing to show you. That's one of your rational function graphs you learned in pre-cal. What? Okay, let me show you something easy and then talk to you about differentiability and I'll be done. Take out your calculator.
So yeah, we can't do this. I don't have my calculator.
Sweet baby Jesus, it's like pulling a
Baby Jesus. Gold.
okay, Ricky Bobby, sit down. All right.
Oh, all these are dead.
Y'all can make me after this. Where is y'all? I had made y'all get calculators from Algebra 2. Where's the calculator?
I have it in my truck. I got it sent and now it's garbage. Can I go get mine from my truck?
I'm just bracing myself right now for y'all. There's one right there for y'all to start fussing. No. You can brain break, but you'll brain break on your own. I'm not gonna stop. Give me. Here's right here.
Where's my boy Quinn Blood at?
Give me one of those one-sided limits we did in the homework. It was like x squared plus x, and we did it as x goes to what? And we found it to be what? 3? Okay. So on your homework, you found the derivative at 1, yes? And the way you did it was difference quotient, right? Watch this. Take out your calculator. Take out your calculator. This is the shortcut before I show you the shortcut. Shh. So remember, only 50% of the test is calculator, 50% is not. But if you get on the calculator part, you have to find the derivative. By all means, do this. Y equals. Put your function into y equals. What do we have? X squared plus x?
57 seconds. Look at there.
After you go into y equals and you have your function, here comes the magic. What did we get when we did this again? 3, right? We're finding the derivative at 1. I haven't done anything. Just second mode, second quit, got out of there. All right, hit math. Go down to number 8. What does that say? deriv. That tells me to take a derivative. Hit in deriv. Yours might, if you have a fancier calculator, I'll show you how to do it. Hang on a second. And in fact, I'll put yours up. All right. If you have an old school calculator like this, follow these steps. If you have a newer one, like a fancy one, and you get something coming up that says d squared dx something something, I'll show you how to plug that in just a second. All right. Give me a second. All right. Older calculators, you have in deriv. You're going to tell it what the function is you're finding the derivative of. To do that, there's a button here that says bars. That's for variables. Scroll over to the y bars and hit function, enter. That says y1 is my function. Your other option is actually typing the function.
I'm so lost. Just do what mine did.
You got to come out of that after you.
But no, even when I did regular, like second quiz,
Help your partner, right? You're struggling.
it's d over d of x.
I'll help y'all in just a minute.
Oh, this is the newer
Same
one?
side, yeah.
Oh.
The same side. All right.
I didn't have one iPad touch me.
It's okay. Sorry. All right, listen. Y1, comma. You're always going to hit an X next. Comma is right above the 7, right above the 7. Sweet. Comma. Where do I want to find the derivative at? When x equals what? 1. It's always y1 x and then the value you want to find it at. Hit enter.
And it gives you 3.
This is great. I'm pretty sure that's a number. Wait, where's the graph?
I didn't graph it. I will show you how to graph it.
No, what graph?
All right, if you have one of these fancy schmancy calculators, did you put it in Y1?
I got the derivative.
All right, you put an X down here because it's d dx. In parentheses, you're going to pull up your same variable. You're going to go vars over to y bars, enter, variables. Right above tangent, right here. Bars. Yep. Then scroll over, x equals, what do I want x to equal? 1. All right. To take this one step further.
You like that? You like that?
I wish it worked. You got 3 types of interaction.
Like that.
Unfortunately, y'all don't have homework today because I have all right. Y'all have been squirrely and you are squirrely yet again.
Hey, I'm ready. But you were sitting there, yeah.
Yeah. Hi, Captain.
No pauses in calculus. We're not graphing today. All right, I wanted to show you that. Now I got one more thing to show you. I'm not surprised. It's probably something not nice. This is a little, one more little thing.
No, I'm telling you, you just see how much time
When
have to.
Oh, you're wasting more time. Yeah, now we're gonna come in.
No, this is quick. This is quick. 4 scenarios where derivatives fail to exist. You just have to know these. I should say derivative fails to exist. Number 1. Is a corner. What is a corner? A corner
It's like when two graphs intersect.
looks like this.
You gotta go back and delete that.
A corner looks like this. It comes in different derivatives. Look at what's happening here. Remember the definition of a derivative. The left-hand derivative has to equal the right-hand derivative at that point. If I am at this point right here, the left-hand derivative is negative, the right-hand derivative is positive. They do not match as I come in on either side. This derivative exists everywhere except at that point. Guys, if everyone talks, I cannot hear. Not at that point. No. Not at that point. Just not at that point. We'll get there. And it just doesn't exist at that point. So if I were to graph this derivative, right? This is negative and it's always the same slope, right? It would be a line. It'd do something like this. That's what the graph of that derivative looks like.
How do you know it?
Because it is a corner. By definition, if the left-hand derivative does not equal the right-hand derivative at a point, and in this case it definitely does not because one's negative, one's positive, then the derivative does not exist.
Not if it was positive and positive.
Right. All right. I told you there are 4 situations. That is situation number 1. Situation number 2 is what we call a cusp. A cusp. A cusp happens when you come in. These are more like rational functions, something like this. It's not a corner because it kind of eases into that value, but it does come in and approach negative infinity or positive infinity there as I come in.
I feel like that's the same thing.
It does touch, but it's not. It looks very similar. But corners and cusp are not. This is what the graph of x to the 2/3 looks like. This is what the graph of something like absolute value of x looks like. Both have, they do touch, yeah. What one? So, all right, so negative, positive, it's going to be really close to No, because it's not a constant, right? So this is coming in close to 0. I have to think about
It
this
would be
one.
like a line, like a linear line.
Hey, that little, the little straight line going like that with the.
Coming in close to 0, but it's getting, yeah, it's going to be something like this. No. But it would kind of have some curve to it. Negative. No, I'm wrong because it's negative and then positive. Yeah. So it's negative and it's going to have some curve to it. Something kind of like that. Yeah. Nope. Because it's getting closer to 0. It's getting closer to 0. Let me show you.
It would be like a line.
Where is my calculator?
It would be like a linear line.
Yeah. Yeah. Not that far. It's gonna do something like that. It's gonna be quite. Okay, you don't. Okay. Oh. Y'all don't waste your time on things we don't need to know quite yet. All right, the other one. Vertical tangent. It looks something like these are things like your cube root that come in, and what's happening is, and this is a terrible, I didn't do it quite justice enough. It comes in and it almost goes completely vertical here in the middle, which would make me have an undefined slope in the middle because it would be a vertical line. Those are vertical tangents. Those come in with your cube roots. That's more of the rational type functions. All your rational functions have funny derivatives. So I'm differentiable everywhere except at that point where there's a vertical tangent. Okay? Yep. So this is not differentiable here. That's my vertical tangent. Right. Last thing is the one that you all said first. Not just an asymptote, discontinuity. Any type of discontinuity is not differentiable. Okay? That could be a hole, that could be a jump, that could anything. This is differentiable, but it is not differentiable at that point. Differentiable anywhere except that point. It could be an asymptote. There's four. Here's one thing that you do need to know. If f is derivative, is differentiable, you know how we have to prove continuity? Yes, we have to prove continuity. If we prove differentiability, we have proved continuity, because in order to be differentiable at a point, it must be continuous. So you can use differentiability to define continuity as well, and you can say because the function is continuous, as differentiable at this point, it therefore must be continuous also. It's just a little Right. Right. All right, let me give you your homework. I did not do good. It was a fight this morning. You did good today. Thanks, White. I appreciate that. Yes.